look at integrals that involve inverse trig when we take the integrals. Okay, in order to do that, we do have a couple of rules that we want to make sure that we copy down. Okay, so these are integrals that end up involving inverse trig. We're only going to take a look at two of them. Let's say we have the integral of 1 over the square root of a squared minus u squared du. That gives us the arcsin of u over a plus c. Let's say we have the integral of 1 over a squared plus u squared du. That gives us 1 over a. That doesn't look like an a. Let's make, oh my goodness. Okay, let's fix that. 1 over a times arctangent of u over a plus c. Okay. The one thing that I will remind you guys of when you have problems like this and you're trying to write this out in terms of u or a is just be careful and make sure your u and a don't look too similar. That can get a little bit confusing sometimes. So again, just make sure that you're being very careful there. These are usually pretty recognizable. The only difficult part is sometimes they may look similar to, say, natural log problems, because remember, natural log, especially with arctangent mainly, natural log problems involve something 1 over something, right, that we're taking the integral of. And your arcsin, sometimes they can get a little confusing and they might look similar to problems with just a plain u substitution with a square root on the bottom. So just be careful. We'll talk about that a little bit later. I'll actually give you a practice assignment that kind of lets you go through the different types just to make sure you feel comfortable figuring out which type of integration to use. But for now, let's take a look at these rules in particular. We're just using inverse trig right now today. So let's take a look at an example of what this might look like. Okay, let's say we have the integral of 1 over the square root of 4 minus x squared dx. Okay, pretty obvious that this one has to be an inverse function, because notice that if we try to make the bottom what's inside the square root our u, we wouldn't have a multiple of our du, right? We couldn't do regular u substitution. So this has to be inverse sign. The square root on the bottom is what tells us it's inverse sign. So our a would be 2. Remember, this 4 is a squared, right? Our u would be x. Remember, it's a squared minus u squared. Okay, so u squared is x squared. That means u is x. So our du would be dx. So if we rewrite this, you can rewrite it if you want to. You don't have to. If it helps you kind of see where everything comes from, this would be 1 over the square root of a squared minus u squared du. Okay, so now if we take that integral, we know that that is equal to the arcsin of u over a plus c. So let's plug back in our u and a. So this is arcsin of x over 2 plus c. Okay, you could take that derivative quickly and see if that ends up working out. Okay, to give you the correct function when you take the derivative to check. All right, let's try another one. Let's say we have integral of 1 over 16 plus 9x squared dx. This is an inverse trig, okay, inverse tangent. Notice that we couldn't do regular u substitution with natural log. We have 1 over something, but if we tried to make the bottom our u and do u substitution, we would not have a multiple of our du. We would have to have a plain x somewhere so that we could have a multiple of our du. So we have to use inverse trig, in this case inverse tangent. Let's start with it. Our a would be 4. Remember, it's a squared plus u squared, so the 16 is a squared. Our u would be 3x. Again, remember this portion is u squared, so u would be 3x. Our du would be 3 dx. Okay, for one like this, it may be helpful to rewrite in terms of a and u, especially because you have to remember to multiply by a constant, because if your du is 3 dx, then we only have a third of that because we have 1 dx. So we do have 1/3, and I'm just going to keep that out front, okay, times 1 over a squared plus u squared du. Now, if we take that integral, we have 1/3, that's just the constant, times, okay, now integral of 1 over a squared plus u squared is going to be 1 over a times the arctangent of u over a plus c. So let's plug back in our values. That's 1/3 times 1/4, 1 over a, times arctangent of u over a, the x over 4, plus c. So we should end up with 1/12 arctangent of 3x over 4 plus c. Final answer for that indefinite integral. Okay. Let's try a definite integral. Let's say we have the integral from negative 1/3 to 1/3 of 12 over 1 plus 9x squared dx. Okay, the first thing I'm going to take care of is simplifying that integral. So let's just take a look at the integral. We're not worried about the bounds yet. Okay, this is going to be inverse trig. Okay, our a would be 1. Our u would be 3x. So our du would be 3 dx. Let's rewrite in terms of u. We have 12 dx, which is 4 times the du. And then we have 1 over a squared plus u squared. Okay, so 4 is just a constant that we're multiplying by. Integral of 1 over a squared plus u squared, that's our arctangent. 1 over a, so 1 over 1 is just 1. And then arctangent of u over a, 3x over 1 is just 3x. Okay, plus c. Now, let's go back to our definite problem. We've taken the integral now, so we know that this is 4 arctangent of 3x. And then we don't need the plus c because this is a definite integral. Let's put in our bounds, our limits of integration. So let's plug in. 1/3 goes in first. So 4 arctangent of 3 times 1/3 would be positive 1, minus 4 times arctangent of 3 times negative 1/3 would be negative 1. So now if we evaluate arctangent of 1, where is tangent positive 1? That would be at pi over 4. Minus 4 times arctangent of negative 1. So where is tangent negative 1? That would happen at negative pi over 4. Again, remember your range of values. So 4 times pi over 4 is pi, minus 4 times negative pi over 4 is negative pi. So minus negative becomes plus, and that gives us 2 pi as our final answer for that definite integral. Okay, I want to do one more. Let's say we have the integral from 0 to 3 of 1 over the square root of 9 minus x squared dx. Again, let's just take care of that integral to begin with. We're not worried about the bounds yet. So let's say, just looking at the integral portion. This is an arcsin. Our a would be 3. Our u would be, oh, that looks like an a. There's a problem. Oh, boy. Okay, we said a is 3. U is x. So du is just dx. So this one is kind of nice. We have the integral of 1 over the square root of a squared minus u squared du. Okay, so that should give us arcsin of u over a plus c. So that's arcsin of x over 3 plus c. Now let's go back over to our definite integral. So this is going to be arcsin of x over 3, and we don't need the plus c because we are evaluating. It's a definite integral. Let's put in our limits of integration. Plug in 3 first, and that gives us arcsin of 3 over 3, which is 1, minus arcsin of 0 over 3, which is 0. Arcsin of 1 means where is the sign equal to 1? That happens at pi over 2. Arcsin of 0, where is the sign equal to 0? That happens at 0. Pi over 2 minus 0 gives us pi over 2. Okay. Guys, we can still do all the same things we've done before with integrals. We can find particular solutions. If we're working backwards, maybe they give us a derivative and a initial condition. We could find average value. We can still do all the same things that we normally do with integrals, except now we just have 2 new rules for inverse trig.